sick, so he decided to go home. To not make us sick. I'm sick of Among being sick, though.
Second order sick.
Okay, so we've been talking about rank for the last lecture or two, and let me remind you what we did. We started with defining tangent vectors, right, as equivalence classes of curves at a point, right? If two curves are tangent at that point, then they are equivalent, and this equivalence class defines a tangent vector. And we defined for any map between two manifolds M and N, we defined its differential by basically taking any tangent vector here, taking any curve that represents that vector, mapping the curve by f to whatever the curve is here, and then the equivalence class of this curve is the resulting vector, which is denoted by f star if this is v, and f star v. And then there was a different point of view where these vectors were directional derivatives, right? We call them derivations at a point. And these derivations can act on functions, right? If this is a function on M, then this produces just a number, which is the directional derivative of that function in the direction of v at point P. And then f star acts on this v by creating a functional, a derivation that now acts on functions on n. So this is a function on n, and then this is just defined as v acting on that function composed with f. Right. This is actually denoted by f upper star phi n. This is pullback of phi n by this function f. So it's basically, if you have a function on this n, you can pull it back, make it into a function on m by just composing it with f. That's called pullback. We will later define pullbacks and these push forwards. For all tensors, but for now it's just for specific tangent vectors. Okay, and then we defined rank of a map in two different ways, and we proved that they're equivalent by proving the rank theorem. So a map has rank R. First, if in some local coordinates, it can be written as this, right? Where M is the dimension of the domain manifold and N is the dimension of the target manifold. And the other definition, equivalent, was that rank, this is at a specific point, and this formula is supposed to hold in the neighborhood of that point. And the second definition, the rank of f at point P, is just defined as the rank of the push forward at that point. Right, these f stars here are actually taken at the point P. So that's the notation for that. Where this is the rank of now a linear operator between two linear spaces, the tangent spaces. So that's well defined as just the dimension of the image of f star P. Okay. Clearly. All right. Yeah.
So is the equal to the rank
Yeah, so this thing basically is the Jacobi matrix. If you write it out in local coordinates, i.e. if you take f star p and you compose it, let's say I have a local chart here, phi alpha, and a local chart here, psi alpha, into Rn, and this is into Rm, right? Then to write this map as a map, you know, in local coordinates, to write it out in specific coordinates, you need to compose it with phi inverse star, whatever the correct point, and then psi star, whatever the correct point. So compose it with the differentials of these guys. And these are already, and the result is going to be a map from T of Rm to T of Rn, but this is just Rm cross Rm, and this is just Rn cross Rn. So now, so now it's just a function between Euclidean spaces, which means it's a specific matrix. We know it's a linear function, right? At a specific point. Actually, I should have written T at a specific point, right? At the point phi of p to the point psi of f of p. And this is just Rm, and this is just Rm. Okay. And it's a linear function, i.e. matrix. And that matrix is literally the Jacobi matrix in these coordinates, if I can say.
So can you think of these pullbacks as just a particular choice of basis for the tangent space and use the chart?
Say it again.
So are these pullbacks, can you think of it as just if you have a chart, it's the natural choice of basis for the tangent space?
I mean, it's not natural, but it's a choice. Yeah. Sure. Yeah. That's actually how we proved that the dimension of the tangent space equals the dimension of the manifold, right? Because local charts are diffeomorphisms, therefore their differentials are isomorphisms of vector spaces. Okay.
Can you remind me about the passwords?
That's the notation for this, for the differential, the push forward. Right. So the differential of a smooth map takes a vector and it maps it to a vector that's attached to the image point, right? So it takes a vector attached to point P and maps it to a vector attached to f of P. Right, so if you think in terms of these curves, right, every tangent vector is an equivalence class of curves. You take any of those curves and you map the whole curve by f, right? And then that's some curve here. And that curve passing through f of p is going to represent some equivalence class, which is called f star p of v. That's just how it's defined. Because it's not the same, right? It's not f, right? So, for instance, in Rn, like in usual calculus, the Jacobi matrix literally does that, because it's the matrix of partial derivatives. So if you act with it on the vector, like imagine drawing a straight line through that vector. If you act with the Jacobi matrix on that vector, you get a new vector. You just think of what derivatives do. It's basically taking that straight line, mapping the whole straight line with f, and then taking the tangent there. Because first derivatives are the same as coefficients of the tangent lines. Okay, so it's called push forward or differential. For now, it's just at a specific point. All of this is supposed to be at some specific points. Alpha is just, I'm just denoting chart maps always with an index because it's like part of an atlas. Side beta, whatever. Yeah, like this whole thing is like, sometimes I denote this by hats. It's like the local representative in charts beta and alpha of the push forward, which is actually the same as the push forward of the local representative. Like I can put beta and alpha on the outside because of the chain rule, right? This is psi beta f alpha, which is f beta star. Okay. Okay, and then remember we talked about the two special classes of maps for which, first of all, they have constant rank, which means that the rank of the differential is the same everywhere, and the rank is maximal, right? And there were two cases, basically. So maximal rank, max rank is the same as rank equal to minimum between the dimension of m and the dimension of n, because the rank cannot be higher than that. And if the dimension of m is lower than the dimension of n, a map of maximal constant rank is called an immersion. And if the dimension of m is higher, then it's called a submersion. And immersions locally look like basically inclusions as like a lower dimensional subset. And submersions look like projections where you kill some of the possible directions. Right? If m is more than r, then you're basically setting those coordinates to 0. So you're like projecting out some of the directions locally. And we also proved the global rank theorem, which is an important theorem that says that if a map is smooth and it has constant rank, and it's injective, then it's an immersion, right? So you don't really need to, for maps of constant rank, to prove that they are in immersion, for instance, you don't need to check that the differential is actually injective at every point. It's just enough to know that it's injective. That's not a necessary condition, but it's sufficient for immersion. And then if it's surjective, then it's a submersion. If it's bijective, then it's a diffeomorphism. That's also a pretty useful theorem. Okay, and for today, we will start by diving into, immersions a little more. So last time we've discussed immersions that are embeddings and topological embeddings. So remember, a topological embedding is a continuous map. Let's say I map the circle into R2. I map it onto some closed curve like that. That's going to be a topological embedding, which by definition is a continuous map, which is injective, and it's a homeomorphism onto its image, right? So the topology that's induced on the circle here as a subset topology from R2 has to be the same as the original topology on this S1 here. right? So for instance, this map that maps the circle to the figure 8 in R2 obviously is not, well, it's not even injective, so it's not an embedding, but it can be an immersion, right? As long as the derivative along the angular coordinate of this map is not 0 anywhere, that's going to be an immersion, because
Inversion or submersion? Inversion is the one which is injective differential.
Injective differential, yeah. So an immersion is a thing that does not collapse any directions, right? Which means that there's only one direction. It's a one-dimensional manifold, so the derivative must not turn to 0 anywhere. So like, as I move with constant speed along the circle, the image point here has to move with non-zero velocity, or it cannot stop anywhere. Then it's going to be an immersion. An immersion is the same as a local embedding. Yeah. Locally in both the image and the pre-image. Okay, but of course it's not an embedding because it's not even injected. And then we also had an example of the straight line mapping into the torus, right? With identified sides that maps it into a straight line like this, like y equals kx, where k is irrational. Then the straight line actually winds like that, and it covers densely the whole torus. And because the image is dense in the torus, the topology, the subset topology induced on it is going to be very different from the original topology on the line. So that's, even though it's an injective map, it's not going to be an embedding. And in the smooth category, we defined embedding maps as immersions that are topological embeddings. So it has to be a topological embedding, but also an immersion on top of that. So derivatives must not turn to 0 anywhere. All partial derivatives, right? Okay. With this, let's define submanifolds. Submanifolds are basically kinds of immersions. So, definition. Let's say we have two manifolds, S and M, and we have an immersion called I. And this whole triple, this entire morphism is going to be called a immersed submanifold, embedded submanifold, and properly embedded submanifold in the following three cases. So number one, S is, I'm going to introduce this notation, immersed submanifold if I is just an immersion, a smooth immersion. Maybe sometimes I will write I above the sign to just keep in mind what the name of the map is. And then it's going to be a triangle like that for embedded. Submanifold. If I is, guess what, smooth embedding. And then S is, actually, like that. It doesn't make a lot of sense. That would have been better. But anyway, properly embedded. Submanifold. If I is a proper smooth embedding. So remember, proper means that the pre-images of compact sets are compact. It's an especially nice kind of continuous map. Why not?
Well, I'm asking, so do we define the rank as can it be, when it's a vector rank, can both connect to the same?
Yeah, then it would be both the immersion and the submersion. Right? So,
Okay. Okay,
that's embedding. So that's all.
Oh, yeah. It's a different morphism, so it's. Notice that I never said that S is a subset of M, right? It could be like a totally separate submanifold. But in most cases where you use these definitions, it is actually a subset. So if it is a subset, if S is a subset of M, then I is just by default taken to be the inclusion map, right? And not just some arbitrary immersion. And then you ask, is the inclusion map an immersion, embedding, etc. If it's not an inclusion map, if this S is just some abstract manifold that is getting mapped into M, then you can think of the image of I, right? You can look at I of S, and you can ask if that, as a subset of M, is now an immersed, embedded, etc. submanifold. And it turns out that if S is an immersive manifold, then the image of S is an immersive manifold of M, as long as that immersion is injective, actually. Is that actually true? 1 second. I know it's true for embedding. For immersion, that could be the problem. Okay, let me be careful with immersions. I'm not sure, but for embeddings, that's definitely true. That embedded submanifolds as subsets are the same as images of embedding maps, because the smooth structure does match in that case. Anyway. Yeah.
So do you believe that if the I here is the inclusion, then it can meet all the three requirements?
Yeah, if it's well, what do you mean by can? Potentially can. So I'm saying if your S, so if S is actually a submanifold, a subset of M, then I is by default the inclusion map. And then, you need to apply this definition to that inclusion map. Right. So it's just sometimes if S is the subset of M, then we will not even specify the map I. it's just by default the inclusion map. Okay.
So even like I is the inclusion map, it is not necessary that I is also the smoothing function.
No, because we don't know what S is, right? It could be some bad subset. Yeah. What?
Or have we defined what superstructure is a subset?
It's a subtle question which I mostly want to avoid because we won't need it very much, but you can do it. But anyway, let's think about this definition mostly, and then apply it to subsets. Also, the codimension of S is defined as dimension of M minus dimension of S. This is not an intrinsic property of S. It depends on M. And here are some examples. Number one, any open subset is a codimension 0 embedded submanifold. That should be clear because the inclusion is basically the identity here, manifold. Basically, but you need to prove that that actually gives you a smooth structure. Okay. If f from n into n is an embedding map, then the image of this map is embedded into n. That's what I said before. And then number 3, if S is embedded into M and at the same time is a subset of M, then S is closed if and only if it is properly embedded. It's kind of a simple exercise, topological exercise. It's a simple criterion for what proper embedding looks like. And finally, if S is compact and embedded into M, then it's actually properly embedded, but that's just because any map, continuous map with a compact domain is proper for obvious reasons. Okay. Now here's a proposition which is a criterion for embedded submanifolds, which is going to be very useful for us. So again, basically, it answers the question: what do embedded submanifolds look like in charts, or what kinds of charts need to exist on the set for it to be actually an embedded submanifold? So a subset S in M is an embedded submanifold if for every point in S, if every point in S has a local, what's called a slice chart, i.e. a local chart phi from some neighborhood of this point. This neighborhood is an open set in M into R M, such that its image is a sliced ball, which means that phi of this neighborhood intersected with S is the set of points of the form x1 through xk and then zeros. Where k is now can be called the dimension of S. And that's it. So if you remember the definition of the boundary of a manifold, for instance, we define the boundary as the set of points which have charts that map to the boundary of the half space in RM, right? The one where the last coordinate is 0. So this is basically the same idea, only there can be more zeros. So the boundary is just by definition an embedded symmetric. Well, because of this proposition, an embedded symmetrical. So in particular, if I give you a set and I specify slice charts for every point, like a whole atlas that covers that subset and consists of only slice charts, then you can show that there's a unique smooth structure induced on that subset, which makes it into an embedded symmetrical.
That smooth structure is just forgetting about those last landscape.
Basically, yeah. But again, you need to check that everything's nice. And that's in the book. Okay. Yeah, so one consequence is that boundaries are always embedded manifolds. So corollary, boundary is always embedded. Okay. Now, here's the first of a couple theorems that talk about regular values in like level sets of functions in general. This one is called the just constant rank level theorem, level set theorem. It says the following: if I have a smooth map between two manifolds, and if it has constant rank R, then the level set F inverse of any point Q for any Q and N is a properly embedded submanifold of codimension R in M. All right. So the proof is very simple because we have proved the rank theorem before. So the definition of rank, the original one, says that for each point in M, we can find local charts in which this F has a special form, right? So by definition of rank, F has a local representative that I'm going to call F hat, which looks like this. So assuming Q is the origin of the coordinate system around it, we can write the inverse. We can write the pre-image of Q locally as the set of points of this form, a bunch of zeros, and then arbitrary numbers here. So these are arbitrary, right? Because so Q is the zero, is the origin, it's the zero, right? So its pre-image consists of all the guys. You know, the first part has to be zero, but then these coordinates, the pre-images of these guys, can be anything, assuming that R is less than M. M minus R, I think. Okay. Let's just say everywhere for now. Okay. So this means that F inverse of Q is a local ball slice, and therefore an embedded semanifold. So this local representative of F basically gives you a slice chart on it, right? Now it is closed. It is closed as a pre-image of a closed set, right? This is a continuous map, so the pre-image and Q is the 1 point set is a closed set, so that's also a closed set, or the whole pre-image is a closed set. Therefore, it's actually a proper embedding, and that finishes the proof. Yeah. Is it true that R? No. That would mean that it has maximal rank. I didn't say it. It's just constant rank, but it can be anything.
It's supposed to be a projection, right? It could be like a rectangle.
R could be 0 for all I care, right? And then it would still, everything would still work. Yeah.
So R is 0, the pre-image is the entire, all of that.
Yeah.
You can check the mathematical sense the whole manifold to a point, and it's still a point is pretty properly embedded.
Okay, so an immediate, yeah. Oh, local representative. I'm just saying, by definition of rank, there exists a local representative that has this. So there exist two local charts, one on M and one on N, which, when composed with F, which is what I call F hat, give you this. For all local proofs, we always use representatives, right? Because then it gets reduced to usual calculus statement. Yeah. Okay, so an immediate corollary of this is that each level set of a smooth submersion is, so let's say Fm into n is a properly embedded submanifold of dimension equal to the dimension of n. I mean, it's just a special case of that, right? Because submersions have constant rank, and we know what it's equal to. And then another one is called the regular set theorem. This is the most famous one, I guess. So every regular level set i.e. a level set of a regular value of a smooth map is a properly embedded submanifold of codimension equal to dimension of n. Okay.
Sorry.
Yeah.
Actually, what is the level set that
The level set is the preimage of any point, right? It's the preimage of a regular value. So if Q is a regular value, then the inverse of Q is a set. It's called a level set of Q.
define the regular value?
So remember, for functions of one variable, for instance, critical points are points where the derivative turns to 0. So basically where it stops being an immersion. And a point on the y-axis is called a regular value if all of its preimages are not critical. So immersions. By non-vanishing, you mean it has to be immersive. It has to be immersive. It's not a square matrix, right? Here. Okay. So this theorem is actually very important. Like in classical mechanics, for instance, when you introduce constraints, like you fix the value of energy in the system or the value of angular momentum or whatever, you need to check that the piece of the phase space that you cut out by adding the constraint is still a nice manifold. And usually, like, you check that the energy function is has a regular value, and the value of the energy that you picked is actually a regular value, then you know that it's level set. The energy surface is going to be a nice manifold, and that's terrible set, which is often not the case. Okay. The proof is also very simple. So remember that the set of all regular points, which in this case is the same as the set where the rank of f is maximal, is open, right? Do you remember that statement that the set of all points where the rank is maximal is always open? Because the set of matrices of maximal rank between two spaces is open in the space of all matrices. So the set of regular points is open in M. So the level set is contained in it, in the set, obviously, together, but it's not just contained in this neighborhood, but in the set, but because the set is open, it's contained in it with an entire neighborhood of itself, right? So with, so let's say, together with a open neighborhood of itself. So f inverse of q is included into some open set u, which is then included into M. And in the middle, it's also included into the regular points, the set of regular points, right? Then f restricted to this open set. The open set is obviously, I mean, if f is a submersion, let's say, then f restricted to u is also going to be a submersion. It's just a restriction to an open set. So is a smooth submersion. So we can use the previous corollary to get the statement. So basically, the statement is that if my f, that if I restrict the domain to a sufficiently small neighborhood of this preimage, then I will get rid of all critical points, and then it'll become a smooth submersion because it has a maximal rank. So it has to be a smooth submersion, right? And then we can use the previous theorem. So this is pretty cool because now we can show that, like, we basically have a new way to construct manifolds. So for instance, now I can say solve this equation in the plane, right? And I claim that the result is a manifold. Why? Because this function, its value 0 is a regular value. You can check by taking some derivatives. And then it's going to be properly embedded into R2, right? So I just proved that the circle is actually manifold. Okay. So things like that you can use for like matrix groups and other things, right, that are defined by equations and not explicit constructions of atlases. And functions like this, if these are scalar functions, they have a special name and they define your embedded submanifold. They have a special name. They're called defining functions of a submanifold. And this next proposition shows that every embedded submanifold always has, at least locally, it has defining functions. So you can introduce like a set of functions which, if they are simultaneously put equal to 0, then the set of solutions of that system of equations will be your submanifold.
So this is like the implicit function theorem, but better.
So all embedded submanifolds, S and M, have local defining functions, i.e. phi, which is C infinity from an open subset of M into R, such that phi inverse of 0 is S intersected with U for some sufficiently small U, which can be a neighborhood of any point. And then second, and yeah, so right before writing this down, I said it's a set of scalar functions, but an equation, a system of equations like this is equivalent to one equation. Right. So this would be one defining function equivalent to a set of defining functions. So one function is always enough. And an immersion is a local embedding. That's what you asked. Immersions are the same as local embeddings, which means that if you're restricted to a sufficiently small neighborhood of any point, then it will be an embedding of that neighborhood with whatever the image of that neighborhood is. Right? So again, the proof of number one is trivial. Take a slice chart. Take a slice chart, which we now know exists always, such that S restricted or intersected with this neighborhood U has the form, just consists of points of the form this, a bunch of zeros, and define phi as xk plus 1 squared plus etc. plus xm squared. And then clearly phi equals 0 defines that set. And number two is was already actually stated before. So I'm not sure what the purpose was of including it here. Okay. And then there's two statements that I'm inclined to not write down. One is extensions of functions, which says that if you have a subset which is an embedded submanifold and you have a smooth function on it defined on the subset, on the submanifold, you can always extend it to a smooth function on the whole manifold, which agrees with the function on the submanifold. And then it's kind of a more generalization of the theorem that we had before about extensions from closed sets to the entire manifold. And then that's for properly embedded, actually. And because if a submanifold is properly embedded, then it's a closed set. And then we can just apply the theorem that we had before. But if it's only embedded, not properly embedded, then the extension is only to a small neighborhood of this manifold, not necessarily to the entire manifold. But anyway, so that's one. And then there's another one, which is not extensions, but restrictions of functions, right? If I have a smooth function on M and S is this manifold, then when do I get a smooth function when I restrict F to S, right? That's the question. And it turns out that if S is an embedded submanifold, then the restriction is smooth. And moreover, if there's an embedded submanifold in N, you can take the double restriction of you restrict the domain to S and you restrict the codomain to K. So you forget about all the values of F that fall into K. And then that also ends up being a smooth function. So I don't think we will need these theorems a lot, so I'm not going to write them down.
Do you want to improve the last one? We just take slice charts and show the differential index is not actual for smoothness,
Yeah, I think all of this is done through slice charts, and like you showed that the local representatives are fine smooth functions. Okay, so we're done with embeddings and with all submersions, immersions, sorry. And now we go on to submersions, which is much more important to us and much bigger because this includes fiber bundles. So submersions. Okay. So let's say I have pi, just any smooth map between M and N, not necessarily submersion for now. Definition, let's define local sections. So a local section of pi is a map sigma from some neighborhood U inside of N into M, such that pi composed with sigma is identity on U. If you remember this terminology from category theory, like lecture 2, we had epimorphisms, and if there was a right inverse to the epimorphism in the sense, that was called a section, as long as it's still a morphism in the same category. So here, the sigma, of course, has to be smooth, right? So for instance, if pi is in R2, pi is the projection onto the first component. It just projects all vertical lines onto the real axis. Then anything of this type will be a section because I take a point here, the value of sigma is this point, and then the value of that point under P is back here. Right, so I get identity. But it has to be a function, right? The sigma has to be a function of from U into M. So this thing as a subset of M has to look like a graph of a function above N. So something like that could not be a section in any sense. Anyway, okay. So so these sigmas are basically generalizations of like graphs of functions. And now here's a criterion for when a map is a submersion in terms of local sections. So the theorem, pi is a submersion if and only if every point in M lies in the in M lies in the image of a local section of pi. So, for instance, here we know that this is a submersion, and indeed, for every point in M, it's possible to draw a section that passes through it. Right? And I claim that if it's not possible for some point, then the map is not a submersion. Right. So again, the proof is pretty easy and based on the rank theorem, of course, because everything is local. So we have in some local coordinates, again, for the forward direction, this map looks like this. Right, it's a submersion, so it's surjective, so I know that there's no zeros in there. And assume P is the origin, as usual. So define in local coordinates, define sigma by this formula. Just basically the inclusion with the necessary number of zeros here. And this is indeed a local section passing through P. And that's it. Okay. So in this direction, it's very easy. For the backward direction, let's say P is an M and sigma is a local section through P. So that means that P is included in the image of that neighborhood in the base, in N, right? The domain of sigma. Then sigma, then P equals sigma of Q for some point Q, and then and pi composed with sigma is the identity on U by definition. Therefore, by taking the differential of this formula, I get pi star composed with sigma star equals the identity on TQU. And let me take this at point Q and this at point P. That's the correct, because P is the image of Q under sigma. TQ of U is of course the same as TQ of N. But now identity is a surjective map, right? Which means that the last one in this composition has to be surjective. Therefore, pi star P is surjective. And by assumption, this is true for every P, so pi is a submersion. Okay. Proves the theorem. So this is a pretty cool property of submersions, right? Submersions are exactly the maps for which there exist local sections passing through any point. Okay. Now, there was a separate type of maps that we introduced in the topology lectures, among the which we called quotient maps. So if you remember, we could quotient topological spaces by gluing points, right? You can introduce an arbitrary equivalence relation between points of a space, and then glue them in such a way that there's like a naturally induced topology on the quotient set. And the corresponding notion of a quotient map, so a topological quotient map, we defined as a surjective and a strongly continuous map. So strongly continuous means that not only continuous, but a set is open if and only if its image under this map is open. Okay. Whereas continuity is only, for a set that's open here, its pre-image is open, which is not the same.
Also, just call it an open continuous map. Continuity is the back direction and open is the forward direction.
No. Open is
if
pre-image of open is open, so it's not.
No, continuity is pre-image open. So open is image.
Oh, open is image of open is open. But it's not the same, right?
Oh, yeah. If
because these guys have a special form.
Yeah. Okay. So this is stronger than open.
This is. Yeah, it's stronger than open. It's not the same. It's weaker than continuous and open. Okay. All right.
So let's see. If it's open, then the image of an open set is open. If it's continuous, the pre-image of an open set is open.
Yeah.
This is saying.
But this is saying that the pre-image of a open set that has this form, which is an image of something, is open, right? So it's not that the pre-image of every open set is open. It's that the pre-image of only open sets of this form is open. Okay. Not every set is the image of something. Okay.
Sort of the constructing courses topology.
The what topology?
So this the idea of the quotient map is to construct the courses topology.
Right. So we had that example where if you take the two-dimensional disk, for example, and you identify all points at the boundary, you get the two-sphere, right? Where this whole boundary gets identified into the pole of the sphere, for example. And this map, the quotient map here, maps every point inside of the disk into like a single point here, but it maps all of these points into the same point. So the pre-image of this one point on the sphere is not an open set in the standard topology. It's a closed set. And if you take, actually, let's check that this map is not open. I can take this neighborhood here, which includes a piece of the boundary, and then does not include these points at the boundary of this disk, right? That's an open set in the topology of the disk, because the topology is induced as a subset topology from R2, right? But the image of this open set will be something like that, which does not include these points, but includes this point, right? Which is not an open set. So it's not an open map, and yet it's a quotient map, because this is still true. If I take the pre-image of this set, it's going to be this plus the entire circle, which is not open, right? So there's no contradiction. Anyway, so that's how we define quotient maps, and we identified them with maps that you get by quotienting sets by an equivalence relation. And the equivalence relation is that you identify all points in the pre-image of every point. These are called fibers above Q, right? So the equivalence relation corresponding to a quotient map is that you identify all points within the same fiber of plane. And here's the proposition of yeah, here's the proposition. The question now is basically, what are smooth analogs of quotient maps, right? These are topological quotient maps. What do we need to add to make this a useful definition in the smooth category? And it turns out that any smooth submersion is an open topological quotient map. So even though in general topological spaces we don't have this nice openness property for quotient maps, in the smooth category it turns out to be true. So we basically forget about quotient maps and we just use submersions instead of them. Right? And we have openness on our hands. Yeah, so when you have boundaries, it's more subtle, right? So let's call the map in question pi, of course, and let choose a point in an open subset of the interior of M, an open subset. Now we can pick a local section sigma through P, because pi is a submersion, and pick a point y in the pre-image of the set W. So pi is going to be yes, from N to N. Okay, pick any point in the pre-image of. Let me draw a picture, maybe. So let's make this whole thing M. Actually, this is M and this is N. Okay, and we have the projection phi. These are fibers. I'm saying pick an open set W in here, in the interior of M. Pick a point inside of it. So W, pick a point P, draw a local section through it. Pick a point in the pre-image of W under sigma, which means over here, right? Pick a Y. Then Y is pi composed with sigma of Y, because sigma is a section of pi, obviously. And this is contained in pi of W, right? Because sigma of Y is in W, so pi of sigma of Y is in pi of W. Okay. This is like surprisingly trivial juggling of symbols. But interestingly, this actually now proves that sigma inverse of W is an open neighborhood of pi of P that's completely contained in pi of W. because we said take a point of sigma inverse in sigma inverse of W, then it's inside pi of W. So the set which is open by continuity of sigma is fully contained in pi of W. Okay, but since pi of P can be any point in pi of W, right? Because W is inside of this, the entire, because P can be any point in W, so obviously pi of P can be any point of pi of W. Then this means that pi of W is open, right? We proved that every point in pi of W has an open neighborhood that's still contained in pi of W. That was our most useful criterion of openness of sets. So this means that pi of W is open, which proves that pi is open. Great. We started with an arbitrary open set in M, and we proved that its image is open in N, so pi is open. That's pretty cool. So, yeah. Well, I mean, it's a bit of a oxymoron here because the interior of M in the topological sense is all of M. Is that important here? I have to think about it. I don't think it's actually important. It's not a submersion. Yeah. Yeah, the example with the disk, not a submersion, because it maps one-dimensional thing into a point, so it collapses some of the directions. There's two directions on the sphere, but you get only 0, like over there.
So if you were to like squish the sphere or the disk into a line, you get the same kind of issue at the endpoints.
At the endpoints, I don't think so, because you have these directions which map onto the same directions just fine. I know it can be, I need to actually check that. So basically, this result leads us to define quotient maps in the smooth category as just submersions. Actually, one second. Surjective submersions, right? Because quotient maps always have to be surjective. Yep.
What is the definition for fiber?
It's the preimage of a point.
Without any requirements.
Yeah, just the preimage of any point. Any map in general, yeah. But if it's a submersion, then we know that it's a submanifold, so that's already pretty nice. Okay. So definition, motivated by this proposition, is smooth quotient map is the same as a surjective submersion. And that's it. Okay. So, like in topology, we proved that if you have a quotient map and you define the equivalence relation by identifying all points in every fiber, then then you can take the quotient of M by identifying all of these fibers, and the topology that's induced from that quotient by the definition of quotient topology coincides with the topology on M, as long as pi is a quotient map. Okay, and that was like an if and only if statement. So here you can prove a sort of a similar statement in the smooth category, which is if you have a smooth quotient map, then it's a topological quotient map, and the smooth structure on N is the unique smooth structure that makes it into a smooth quotient map. Okay, so so the smooth structures that you can induce by quotienting M also agree with the ones that you have on N. But that's not going to be super important to us. They are submanifolds, right? We know we had the submersion rank level set theorem. Yeah. So this leads us to this table that I've already drawn before, which was we have immersions, we have submersions, we have the nicer versions, which were injective immersions. And here we have quotient maps, which are surjective submersions. Right, nice symmetry. And then we have even nicer versions here. What's even nicer than an injective immersion? Embedding, right. Well, embedding, proper embedding. And what's even nicer than the quotient map? That's yet to be learned, so that's fiber bundle. And that's basically almost the next thing. So we start with the topic of fiber bundles with kind of the baby version of fiber bundles, which are covering spaces, right? If you've ever heard of like spin groups and the fact the spin groups are covering spaces of SO3 and whatever, that's what that is. So the main reason why I even include this into these notes at all is because at some point we will get to Clifford algebras and spin groups, and it's nice to mention that to define the spin groups this way, although it's not really necessary. Covering maps are going to be very special classes of a very special class of quotient maps. Much more special than fiber bundles, right? A special class of fiber bundles. So definition, we start with defining the topological quotient map. It turns out that for covering spaces, covering maps, there's basically almost no difference between the smooth and the topological case. So I'll just focus on the topological case. Topological covering map. So a continuous map pi from E into M onto M, where E is called the total space. This is called the base space is a topological covering map. If it is surjective and every point in M has an open neighborhood U sub P, such that pi inverse of U sub P, the preimage of that neighborhood, consists of at most countably many connected components. Countably many connected components, which we will denote U tilde sub I, and each restriction pi to these U tildes is a homeomorphism. No. But from this definition, it should be clear that they are basically required to be connected here, because one of these is connected and it's supposed to be homeomorphic to U. So sure. But that doesn't work here because that cannot be homeomorphic to these guys, which are required to be connected. That just happens automatically by the definition. It's a statement of there exists a U sub P, which is homeomorphic to a connected set, so it has to be connected. Okay, so to immediately give you a visual example of what's going on here, this is basically going to be the prototypical example for us. Let's take the circle and the real line. And there's a covering map between R and the circle, which can be drawn this way. You draw like an infinite spiral in 3 dimensions, and you just project it vertically onto the circle. Okay. The spiral is, of course, homeomorphic to the line. This is clearly a submersion. And for every point in the circle, I can find a small neighborhood like that, such that its preimage consists, consists of these guys, right? Countably many neighborhoods, connected neighborhoods, each of which is homeomorphic to this one. So that's the entire definition. Countably means
Countably infinite, right?
countable is cardinality of natural numbers, right?
What if we were to do something like somewhat topological here, like say make, in this example of projecting a spiral map, we make each rung of the spiral progressively closer and then add another point. Would that still work? I just can't think of why it would.
That still works, right? You'd still have countably many, they would just get really close together.
Is the topology in that different from R? It seems to be different from R. I'm pretty sure something is supposed to break in that example. Okay. Of course, you can have disconnected covering spaces, so like a circle, and then like 2 circles above it, or 3 circles, right? Disconnected with the projection. But we will not really consider those in most cases, because you can just take them separately. Or I can have like a double cover of the circle, right? Which comes back to itself. So it's basically the boundary of the Mobius band. If you imagine that in 3D, you can project that onto the central line of the Mobius band, to the equator of the Mobius band, and that's a double cover of the circle because there's two sheets. So double cover. All right. So what can we say about covering spaces based on this definition? Well, first of all, in the smooth category, a smooth covering map is everything is the same, only pi now has to be not just a surjective continuous map, but a submersion. And this has to be diffeomorphisms. That's it. Okay. So the total space is going to be locally diffeomorphic to the base. Everywhere locally diffeomorphic to the base. All right. Proposition. For any covering map pi, the following properties hold. Number one, the neighborhood UP in the definition is connected, has to be connected. We already explained why. Then covering maps are local diffeomorphisms, submersions, open maps, and quotient maps. So all of the above, basically. If pi is a covering map, pi is injective, then pi is a diffeomorphism. So it's a trivial covering map. And number four, for a point in the fiber, actually, okay, in the point, for a point in the fiber of some point q, and uq as in the definition, there exists a unique local section, sigma up uq into e through p, i.e. sigma of q equals p. So in this example, that's fairly obvious, right? If this is my q and this is my p, then there's only one local section, which is literally just the inverse, the local inverse of pi. Because pi is a local diffeomorphism, locally it has inverses. And that's the only sections you can have. So the statement is that those are unique local sections. Which is very different from a general fiber bundle, right? From a general submersion, where there can be many different sections you can draw through a given point in the total space. All right. So basically, the only thing I need to prove, well, number three, if pi is injective, then we also know that it's a submersion already, so it has constant rank. And we have the global rank theorem, which says if a map has constant rank and it's an immersion, then it's and it's injective, then it's an immersion, right? And now it's an immersion and a submersion at the same time, which means it's a diffeomorphism. Okay. And then number four is the only thing we need to prove. So first of all, the existence of a section is guaranteed by definition because it's a submersion, for example, or you can take the local inverses of pi to be your sections. So uniqueness, let's let u tilde be the connected component of pi inverse of uq that contains p. Okay. Then pi restricted to this u tilde is a diffeomorphism by definition, whose inverse is a section through p, defined on u, defined on u, q. Now suppose there's another section sigma prime from uq into e, also through p. What does that mean? Huh? Why? What? Why?
If you simply differ
Okay, so so let's do this correctly, carefully. So then sigma prime of uq is contained in u tilde because uq is connected and sigma prime of q is p. Okay. But then both sigma and sigma prime are right inverses of the bijection pi restricted to u tilde. Right now, this is a homeomorphism, therefore a bijection. So its right inverses have to be the same. So that proves uniqueness. And this property basically leads us to probably the most important property of covering maps, covering spaces, which is sometimes known as, like in complex analysis, it's known as the monodromy theorem and stuff like that. So here it's called the path lifting property. You can actually use it to define covering maps. And this is the following. Let me actually show you on the picture first, and then formulate. Let's say I have this spiral. Right. Let's say I pick a point P in the base, and I draw a path that starts from P. Okay, so I draw a path that goes maybe something like that to some point Q here, right? And this path is gamma. In the fiber above P, I have a bunch of points, an infinite number of points. Let me choose one of them. Okay, so let's call this P0 or something. I'm pretty sure I'm going to rename these in a second. Let's call these P0. And I want to do the following. I want to look for a path in the covering space which projects onto this one, right? So pi of, if this is my gamma, then pi of this lift, gamma of tilde, at every point t has to be gamma of t, right? With the property that gamma of 0, gamma tilde of 0 is this given point. So this is the only choice I have here. I claim that this path exists and is unique always. So in this picture, if I follow, I have to go in this direction. It's a local diffeomorphism. So the only thing I can do is just follow the spiral here, right? And then stop. Stop in the fiber above Q. Okay. So my new path does this. This. And I claim that this property is true for all covering spaces. So all paths in the base have unique lifts to the total space as long as the beginning point is given. So the statement is, let's say this is a cover, i.e. a covering space, but gamma would be a path in M. Pick a point P in the fiber above the starting point of gamma. Then there exists a unique path gamma tilde from 0, 1 into E such that gamma tilde of 0 equals P and pi circ gamma tilde equals gamma. We call gamma tilde the lift of gamma. Okay. And the proof is an exercise. It's a very simple proof, at least in the topological category, because we know that pi is locally a homeomorphism, so there's only one way to lift it locally, right? The only matter is then you need to stitch them together, check that they do stitch into a continuous path, and that's it. Uniqueness follows from just the fact that pi is a local homeomorphism. Okay. Yeah. So in complex analysis, this is used for analytic continuation, for example. If you have a domain where your function is an analytic, let's say maybe this domain has an angular shape, like it has a hole in the middle, and I have I have a path over here, then you can think of kind of the Riemann surface of any analytic function on this domain, like log z, right? If this is 0, I can consider log z as long as there's a cut. And it's a Riemann surface that represents the graph of that function. Then the claim is that there's a unique way to analytically continue the function along this path. So you'll, given a starting point, given a choice of the branch of the function in the beginning, you will always get a unique value at the end of the analytic continuation, even if in general this map is multi-valued. So like log z has many branches, right? But if you pick a branch and analytically continue from it along some path, you will end up at a unique value in the end. There's a unique lift. And the proof is very simple. It's analytic, therefore it has a Taylor series at every point. So there's a Taylor series here that converges in a finite radius. So we can move a little bit from there. This point has a Taylor series that has a finite radius. We can move more. And obviously this is going to cover the entire path because the function is analytic everywhere in the neighborhood. And in a finite number of steps, you will end up there. And the Taylor series gives you a unique value at every step. So, so this is just the topological version of that.
Somewhat related question related to that. So at no point did you mention the discrete topology. Is it true that the fibers of every, or is it true that the fibers will always have this topology?
Yeah. Mm-hmm.
Okay.
You can think about that.
And,
Okay. And yeah.
So you have mentioned that which functions may be multi-level here.
I will actually give example. Well, I guess next time I'll give examples with analytic functions. It'll become clearer, hopefully. But yeah, like e to the z, for example, is a covering map which maps c star, c minus 0. Sorry, it maps c onto c star. It's an infinitely sheeted cover of c star. If you restrict this to the circle in the complex plane, you will get exactly the infinite spiral. No, sorry, not the circle, the imaginary line, right? There are. Then this will be exactly the spiral map e to the ix, right? Maps real line onto a circle. So e to the z is just like an extension of that. It's like a helix made out of a complex plane mapping onto the complex plane.
you could say that any smooth multi-value function where the values of each given point have where the image of each point has the discrete topology would automatically have.
Yeah. Mm-hmm. Okay. So here's the monodromy theorem, which is a stronger version of this. It says that if I now take this path in the base and I homotopically deform it, continuously deform it by homotopy, then the lifts of the two paths, at the beginning of the homotopy and at the end, will also be homotopy in the total space, and they will have the same ending points. So this is called monodromy theorem. Let's say we have gamma 1, gamma 2, paths in M with gamma 1 of 0, gamma 2 of 0, gamma 1 of 1, gamma 2 of 1. Okay. Same ending points. And let gamma 1 tilde, gamma 2 tilde be their lifts with gamma tilde 1 of 0 being equal to gamma tilde 2 of 0, so with the same starting point, which I'll call P in E. Then gamma 1 tilde is homotopic to gamma 2 tilde if and only if gamma 1 is homotopic to gamma 2. And number 2, if gamma 1 is homotopic to gamma 2, then gamma 1 tilde of 1 is equal to gamma 2 tilde of 1. So if I homotopically deform a path, I cannot change the endpoint. This homotopy is required to be with fixed endpoints. Of course, on the circle, I can take this path and homotopically deform it into this path by just stretching it out. But I want to fix the endpoints for this homotopy. And the proof of this is also an exercise. bit easy for all the same reasons. Okay. So I will probably stop around here, but here's a fun remark about this. This whole story about the path lifting property and homogamy theorem is the first example of a connection for us. Like in part 3 of the seminar, if it ever happens, we're supposed to discuss principal bundles and like connections and gauge theory, right? So this is like a trivial example of a connection because a connection is a prescription for how to lift paths. So I have the base and I have the fiber bundle above it, let's say a covering space in this case. I draw any path in the base. I'm supposed to, given a starting point in the total space, I'm supposed to be given an instruction for how to draw a unique lift of that in the total space, which is going to be called a horizontal lift, right? So it's basically a way to tell which directions in the total space are horizontal, i.e. parallel to the base. And if you take a tangent vector in the total space and you transport it along the path by just, proclaiming that all tangent vectors to the lifted path are parallel to each other, that process of dragging that vector along the lifted path is called parallel transport, right? That's what happens in Riemannian geometry, for example. And here, it just so happens that there is no choice of a connection. So for covering spaces, the connection is unique, right? The path lifting property tells us that there's only a unique way to lift paths from the base into the total space. Whereas for a general fiber bundle, like this projection fiber bundle of a square onto a real line, I draw a path here, I can lift it in many different ways. Whatever. There's many different things that can happen. So an infinite choice of connections. In this case, they're actually all gauge equivalent. But in a covering space, there's a unique connection. Right? And moreover, it's a flat connection. What does flat mean? So yes, so a flat connection is a connection where if I draw, let's say this base is 2-dimensional and this is like 3-dimensional, then if I draw a contractible loop in the base, right, and I lift it to something here, in general, it doesn't necessarily lift to something closed, to a closed loop, right? Like my horizontal directions could lead me to a point that's in the same fiber, but it's not the same point, like it's shifted by some vertical distance. And that effect is called curvature. Like if there's a difference between the ends of lifts of closed loops, that's called curvature, right? But if there is no difference, if it actually lifts to a closed loop for every contractible loop in the base, that's called a flat connection. And here, that's true because of this theorem. So why this is actually all related to curvature and the gauge theory, etc., we will find out much later. But,
Number 2, we go with fixed endpoints. Is that not supposed to?
it means that, so it means that the homotopy is done in the class of maps of paths whose endpoints are the endpoints of these guys, right? So if it was a curve that went from P1 to P2, then I'm only allowed to deform it like that. I'm not allowed to change the endpoint to something else. In this case, yeah, but I didn't specify that also in the entire homotopy. That also has to be true, right? Like the homotopy is a thing that's a function of 2 variables, time and my point. And I'm just saying this homotopy at time equals to 0. Actually, there's like 2 times Okay, this has to be gamma 1 of tau, and homotopy at 1 tau is gamma 2 of tau, right? But this doesn't say that in addition, h of t0 has to be gamma 1 of 0, and h of t1 has to be gamma 1 of 1 for all t. That's like an extra condition that in the process of deformation, the endpoints don't change. Okay, so I thought this was like a neat connection to connections and flatness. We will actually talk about flatness more next time. Yep. And then we'll discover that covering spaces are exactly fiber bundles with discrete fibers. Other than that, there's no difference.
What's the problem if you choose, like, say, just as a simple example, the realigned times power to 2 plus 0, so almost discrete space with one level point. Like if you take the real numbers power to 2 and 0, then that doesn't have the discrete topology, right?
Oh, you mean like including negative powers?
Yeah.
Like a comb where the teeth get very close together.
Sure.
Yeah, and then you take the product of those topology and the same real line. Then we'll keep that from being a fiber bundle. So it seems like it's still not possible to jump between the sheets, if you will.
Yeah. I mean, I think there's no local homeomorphism. If you take the top sheet, I think pi restricted to that is not going to be a local homeomorphism. That's the problem, right? Because an open neighborhood will include like the neighboring sheets. And there's no way to get rid of them. So that also explains why the topology on the fiber in that case is not discrete, because it's not a.
The only way to fix that is just make that
Okay. Thank you. Next time, we'll finish covering spaces and start fiber bundles. Yeah.
Wait, what would I do? I would ask someone to get me stuff. I mean, the teach is cool to start with, like after a 4-hour lab. Can't
Or
drink
maybe you can eat outside of lab.
But then-
5 minutes and no one will notice that.
Yeah, I guess. You set up a little pizza table.